All right, what do you think about for the first one? Not like which answer, but what's it asking here? Go ahead. Do you have your hand? Okay, no. What were you thinking about for the first one? Like, what were the discussions here? Yeah, go ahead.
The weakest bonds.
The what?
Weakest bonds.
The weakest bonds. What would the weakest bonds? How would the weakest bonds contribute to the number of dissolved particles?
The weaker the bonds, the easier it is to break up.
Okay. Yeah. So the idea is what happens to these things in solution. So let's take the first one, potassium chloride. You put potassium chloride in water, what happens to it? It breaks up into two ions, potassium ion and chloride ion. So that's what we talk about when we look at those total ionic equations. We know that in water, in solution, this is going to be potassium and chloride. Okay. So what about K2SO4, potassium sulfate? What happens to that in solution? Sulfate and potassium. Two potassiums, right? Because they both break up. Also aqueous. So which of those two produces more dissolved particles per mole of dissolved solute? B. Because each mole of KCl produces 2 moles of dissolved particles, a mole of potassium ions and a mole of chloride ions. But each mole of potassium sulfate produces 3 moles of ions, 2 moles of potassium and 1 mole of sulfate. What about C then, glucose? What happens to that? Yeah, nothing. When you dissolve glucose in water, it's not ionic. It's a covalent compound. So the equation for the dissolution of glucose looks like this: C6H12O6. That's like solid glucose, like sugar. Well, it's not table sugar, but glucose. If it dissolves in water, it just becomes C6H12O6 aqueous. But it's not ionic, so it doesn't break apart. So every mole of glucose that you have in solution still just has 1 mole of particles in solution. And then finally, what about ammonium phosphate? What does that do? Is that ionic or covalent? It's ionic. So what ions does it break into? Yeah, ammonium and phosphate. So that's going to give us 3 ammoniums and a phosphate. So which one has the most number of dissolved particles per mole of dissolved solute? It's got to be D. D is giving you 4 moles of dissolved particles per mole of solute. And we talk about, when we get into the solutions chapter, or if you go into the health fields and you talk about things like osmotic pressure and how that affects the blood and like IV solutions, that kind of thing, this is really important because even though you might have a mole of ammonium phosphate or a mole of potassium chloride, that's going to give you a different ionic concentration in solution because one of them makes more ions than the other when it dissolves. All right, so same question here, number 2. If you look at those choices, which produces the largest number of dissolved particles per mole of dissolved solute in this case?
A.
Why A?
Because it looks like a CO3 and 2 case.
Yeah, so that's 3 moles of ions per mole of solute. Which one has the fewest number of dissolved particles per mole of dissolved solute? Why sodium iodide? It's what? No. Well, how many? Okay, guess. How many particles does sodium iodide form? How many moles of particles would sodium iodide form? 2. Any of these other ones produce 2? The last one would, right? Ammonium chloride would produce a mole of ammonium and a mole of chloride. So those 2 would be the same. What about C? What's C?
Maybe 2 or 1, I don't know.
Yeah. Is CH3 an ion? It's not. So this is a covalent compound. It just makes 1 mole of particles per mole of solute. That's methanol. All right, now let's try the same question, but now we're going to actually quantify it. So if we have cobalt chloride now, and we're given a specific amount, 0.27 moles, how many total moles of ions are produced when it dissolves in water? How are we going to do a problem like that?
What you said, Mercury.
Yeah, we need to think about how many total ions are released. So we could even do it like a conversion factor. We could say that 1 mole of cobalt chloride, cobalt 2 chloride, gives you 3 moles of ions. Because the cobalt and the chloride are all going to break apart, and that's 3 ions per formula unit. So we could say, all right, if we start with 0.27 moles of cobalt chloride, and we want to convert from moles of cobalt chloride to moles of ions, that's 3 to 1. So we'd multiply that by 3, and you get 0.81. All right, try this next one on your own. Similar problem. And if you get that one, try number 4 or number 5. Oh yeah, sorry. Yeah. You're looking for ions. So if there are, if it's a metal and a non-metal, that's the easiest way to tell, because that's always going to be ionic. Or if it's all non-metals, then you look for the polyatomic ions. If the polyatomic ions are present, then you know it's still got to be ionic. So like ammonium phosphate, NH4,3PO4, that's all non-metals, but we can recognize that NH4 is ammonium and PO4 is phosphate, so we know that that's made of those ions. I guess the other kind of exception to that is acids. So acids are also form ions. Strong acids also form ions, like hydrochloric acid, sulfuric acid. So we have to recognize those as well. All right, so looking at this number 4, what'd you come up with? D. So you need 4 times that number of moles because you've got 4 ions produced by each formula unit of ammonium phosphate. Good. All right, so now we take one more step here. How many moles of hydrogen ions are present and 750 milliliters of 0.65 molar hydrochloric acid. So what's the extra step here that we have to deal with? How is this question different from this one?
You have to go from molarity to moles.
Yeah, so instead of being told a certain number of moles of HCl, we're told a volume and a molarity of HCl. But since molarity is moles per liter and we're given liters or milliliters, we can figure out the number of moles of HCl. So we would say 700, well, let's just convert that to liters, 0.750 liters of HCl. And then the molarity tells us it's 0.65 moles per liter. So we've got 0.75 times 0.65 is 0.49 moles HCl. All right, and now we've got a decision to make, although the choices make us not have so much of a decision. But how many moles of hydrogen ions are present in 0.49 moles of HCl? Is it 1-to-1 or is it different like the previous problems? It's 1-to-1 because every HCl unit has one hydrogen. If that were H2SO4, sulfuric acid, then we'd have to multiply by 2 because there'd be twice as many H pluses because it's H2SO4 instead of just H. So this one, again, same thing. Do you have to know the formula for nitric acid to solve this problem? Probably a good idea. I guess you don't like technically need to, but what is the formula for nitric acid? Close. Which ion does nitric acid come from? NO3, nitrate. And what's the charge on that? -1. NO3 is -1. So how many hydrogens does it need to balance the formula? 1. So nitric acid is HNO3. If you think about them as coming from the ions and you know your ions, which hopefully you do at this point, then you should be able to find the formulas. So all we need the formula for in this case is to know that there's one hydrogen per formula unit. So when we solve it the way we did before, we have the same, we don't need to take an extra step there. It's 1-to-1. All right. Let's find one more version of this type of a question. Kind of puts it all together. The top one on the next page. How many sodium ions are present in 325 milliliters of 0.850 molar sodium sulfate? So you've got a solution of sodium sulfate, and the question is ultimately asking for sodium ions. So not moles of sodium ions, not moles of total ions, just sodium ions. So see if you can figure out how many sodium ions are present in that solution.
Number 11. Will be able to give me that answers.
Yes, we're going to look at that next.
Okay.
No, you never need to go to grams here. So you would, once you figure out moles of individual sodium ions, so you've got moles of sodium sulfate there. All right, and so then you need to get to moles of just the sodium ions. Then it's right, and then you go to the Avogadro's approach.
Oh. Oh. That's all. Yeah. It's pretty fun. Awesome. Pretty well. You laugh. I guarantee you watch those videos. I guarantee you have to be there.
All right, let's look at how we would go through this one. So once again, we have milliliters of a certain concentration solution, and we ultimately want sodium ions. So our plan is going to look like, hopefully at this point we can just go to liters in our heads. So we're going to go liters to moles of sodium sulfate using the molarity. Then we want moles of just sodium ions, because we know how many sodium ions are per formula unit. And then we can get to ions using Avogadro's number, because we know how many are in each mole. So once we have moles, we can get to the number. So that looks like this. 0.325 liters of solution. And then the concentration of our solution is 0.850 moles per liter, and that's moles of sodium sulfate. And then if we look at the equation, we see that there are 2 sodium ions in every formula unit of Na2SO4. So 2 of those in each one of those. And then we can use Avogadro's number to get the total amount. So we put that all together. 0.3, yeah.
Why do you have to go to liters? Is it just because it's like the original?
Because of the definition of molarity. So molarity is moles per liter, which means if we left it at milliliters, we'd have millimoles. So you can actually use, depending on how I don't want to confuse anybody, so just tune out at this point if you're concerned, but depending on how the question is set up, you can use milliliters, but then you get the answer in millimoles. And sometimes that's helpful. Like if you're going to convert it later anyway, you can think of molarity as millimoles per milliliter or moles per liter, but not moles per milliliter. You'll be off by a factor of 1,000.
Like the term millimoles.
Yeah. When you're using like small quantities in the lab, like normal lab quantities, we use millimoles a lot. Just because it's a more convenient measurement. Instead of always saying like 0.08 moles, you can say 80 millimoles. All right, so multiplying this through, 3.33 times 10 to the 23rd, so that's B. All right, so now let's look at the next one, which is kind of the same kind of question that we've just been talking about, but it's worded very, very differently. So this time it says, which of the following solutions will be the best conductor of electrical current? How would we figure that one out? Yeah.
Which one divides into ions?
Yeah, so this is actually the same way of asking the question, which one produces the most ions in solution? because the more ions that are in the solution, the more charged particles you have, the more electricity can move through a solution. That's why salt water conducts electricity, but sugar water doesn't, because sugar doesn't produce ions in solution. So of these four, which one produces the most ions in solution? C, yeah, C is actually the only one that produces ions in solution, right? The rest of them are all covalent. So that's the only one that's going to be electrically conductive at all. Same type of question. Which one do you expect to have the lowest electrical conductivity in this case? Of those five choices. Why ethanol? Yeah, it's a molecular or a covalent compound. Everything else here is either an ionic compound in the case of A and C, or what are D and E? Yeah, those are both acids, acetic acid and perchloric acid. And those are both going to produce ions in solution as well. They're going to make H+ ions and acetate or chlorate ions. So only B really is completely non-ionic. So electrical conductivity is one way that we can test how ionic something is, or how many charged particles it's putting in solution. Okay. So I want to jump down a little bit here. There's a bunch of practice for equations here. We'll go through that when we have time at the end. But I want to look at a question like this based on the solubility rules, but without looking up the solubility rules. Because we got an exam on Monday. I don't know how much space you've got in your brain this weekend, but if it's a choice between remembering ions and remembering solubility rules, you got to go with ions. That's way more important. And as long as we know a few things about solubility rules, we should be able to figure out something like this. So select the precipitate that forms when the following reagents are mixed. What do you think? So first of all, what's going to happen in this reaction?
Double displacement.
It's a double displacement, so we're going to switch ion partners. Magnesium is going to go with hydroxide, and lithium is going to go with acetate.
Yeah.
Close, yeah, acetate. So assuming that one of those is indeed a precipitate, which is likely to be insoluble? Lithium acetate or magnesium hydroxide? Why?
So I mean, hydroxide. Actually, no, opposite.
Opposite?
Yeah.
Why opposite?
Because there's no alkali salts.
Yeah, so as long as you know that rule that alkali metal salts are always soluble, you can at least make a good guess that magnesium hydroxide is probably the precipitate. Does everybody see that? So lithium acetate, whether or not you know about acetates, if you know that all those alkali metal salts are always soluble, then you can immediately say, okay, that lithium acetate's got to be soluble. So if there's a precipitate, it's got to be magnesium hydroxide. Now, if there were a choice in this question that said no precipitate is formed, then you really got to know all the rules, because then you got to know that hydroxides are usually insoluble. That's a much more difficult question. So magnesium hydroxide, is that C or D? D, how do you know?
Because magnesium is a +2.
Right, in the second column, it's a +2 ion. So it needs 2 hydroxides. Okay, next one, same question. Now we don't have an alkali metal. Let's see if we can figure it out anyway. You want to make a guess? Copper sulfide? Yep, that's right. We'll talk about which. How do you know it was copper sulfide?
Because the other product, ammonium nitrate,
Yeah.
that would be soluble.
Yeah. What rule are you using to know that ammonium nitrate is soluble?
Sure.
Okay. That's another one to remember. Ammonium, NH4+, actually acts a lot like an alkali metal ion. In fact, it's used in a lot of situations where you want an alkali metal, but with some slightly different properties. So NH4 plus can make a lot of the same compounds as alkali metals can, and so it's also always soluble. Ammonium salts are always soluble. And actually nitrate salts are always soluble too. So if you remember your alkali metals and the pseudo-alkali metal ammonium, and then you remember nitrates are always soluble, that gives you a good chunk of them, even if you don't know all the other specific rules. So second part of this then, which copper sulfide is it, A or B? A, why A? Yeah, it's copper 2 nitrate. And in a regular precipitation reaction, we don't have any redox chemistry going on. There isn't any oxidation and reduction. So we assume that the metals are going to keep their same charges. Okay, great. Let's move on. Let's take a look at this one right here. So in a multiple choice format, there's not going to be a question that just says, what's the name of this ion? Or write the products of this reaction. It's got to be multiple choice. So this is one way that this might be asked in a multiple choice format. What is the name and chemical formula for the precipitate formed by this reaction? So take a look at it. See if you can figure it out, and then we'll talk about it. All right, everybody got an answer? What'd you go with? How many people went with A? B? C? D? So then just a bunch of not sure's. All right, how did you come up with A? Somebody who picked A. You want to describe that?
I mean, sulfate is 2 minus,
Yes.
so it has to be cobalt 2.
Right.
Sulfate. So. And you know that ammonium is soluble, so then therefore cobalt phosphate has to be precipitated. I think it's obvious because that's all the choices you get. So because cobalt 2 is plus 2, and phosphate is 3 minus, you need to do cobalt 3 phosphate 2.
Right, yeah, thank you. So A has got to be right because you've got cobalt 2. It's not a redox reaction, it's a precipitation reaction. So we're not changing charges or oxidation states. So cobalt stays cobalt 2. We know phosphate is minus 3. So in order to balance those, you got to have 3 cobalts for 2 phosphates. All right, great, thanks. Okay, there's some more of these to practice. I do want to look at one more before we go on to something different. Let's take a look at this one right here. These are the tougher types of questions because of that answer D, no reaction occurs. So you've got to really think about what's going on here, what type of reaction this is, and what the products might be. All right, so I'm not going to ask you for answers on this one, but how did you think about it? Yeah.
It's, there's an acid reactant, so it produces
So it produces what?
no precipitates.
Right, so we see an acid as one of the reactants. That's one of the big clues here, is that HNO3 is a strong acid, nitric acid. And so that puts it in a couple categories. It can either be an acid-base reaction, which is probably the most likely, or it can be one of the other ones like a gas evolution reaction or a redox reaction. Probably not a redox reaction in this case because we don't have a metal or anything in its elemental state that the acid is reacting with. So we got to look at either an acid base or gas evolution. Can you rule out gas evolution here? You can. Why? Well, you're making water, but what if you didn't know that at first? Because you make water in the gas evolution reactions too.
As long as there's enough oxygens.
Sure, but you can always balance the equation if that's necessary. Do you have another?
I was gonna say there's no carbon.
There's no carbon, so this goes back to, yeah. Yeah, carbon's not the only thing that can evolve gas, even though that's what we did in lab yesterday. There's a few others. There's sulfites, there's ammoniums, but nitrate is not an ion that breaks down into a gas-forming type of thing like NO. I mean, yes, you can make NO2 from nitric acid, but that's a different kind of a thing. So the best answer here is going to be B. So we're recognizing that we've got an acid and a hydroxide, which is a base. So if we do the regular double displacement trade partners thing, we're making water and barium nitrate. So B is the best answer here. All right, let's practice this oxidation reduction, then we'll get into this calculations before here. Sodium metabisulfite, which is a compound that's used in a lot of ways, but one thing it's used for is to stop fermentation and brewing and other types of alcohol manufacture. What is the oxidation number of sulfur, or the oxidation state of sulfur? So remember, sulfur is not a metal, it doesn't have a charge. In fact, that's a polyatomic ion, S2O5, but we can still calculate an oxidation number. So see if you can do that. Remember the priority rules here. We're going to look at the metals first. Sodium always is +1. And then go from there. All right, what'd you come up with? C +4? isn't it different? So we're going to go 2+ for the sodium. And then oxygen, we say gets priority, which just means that oxygen is more likely to be -2 than anything else than sulfur, which can have a range of different states. So we would calculate the oxygen next, which is -2. We assume it's -2. So that's -10 total. And then take away those 2 from the sodiums, means the sulfur has to be responsible for +8. So there's 2 sulfurs, each one's +4. There's your +8. So that's going to be +4. So that one here. This is a tricky way of asking this question, so let's talk about this one. This is a redox reaction. You don't have to figure that out. It's told you're told that. But the question is asking you to look for the oxidizing agent. What is the oxidizing agent? Yeah, so you kind of have to flip that around in your head a little bit. The oxidizing agent is the thing that does the oxidizing to the other thing. So it is itself reduced. An oxidizing agent is something that is reduced, and a reducing agent is something that is oxidized. So you really got to read the question carefully, because if the question asks, which compound is oxidized in the following reaction, or if the question says, which is the oxidizing agent, that actually has the opposite answer. So in this particular one, which one is the oxidizing agent? Which thing is getting reduced? Let me see it. A, yeah, because mercury is going from 2+ to 0. So that's a gain of electrons, 2+ to 0, so that's reduction. So mercury 2+ is the oxidizing agent. Generally, the oxidizing agent will be the one in the higher oxidation state to start with. Not always the case, but usually. The other way to remember that, unless this confuses you further, but sometimes it's helpful, where does that word oxidizing come from? Oxygen, yeah. Oxygen is a great oxidizing agent. That's where the name comes from. Stuff being exposed to oxygen gets broken down and gets oxidized. So oxygen oxidizes stuff. Oxygen is always the oxidizing agent. What does oxygen become when it reacts? So if it starts as O2, which is a 0 oxidation state, what is it usually then after it does whatever it's going to do? What's the usual charge on an oxygen ion? -2. So oxygen's usually going from 0 to +2 when it oxidizes things. So that's an example of what's happening there. When oxygen acts as an oxidizing agent, it goes from 0 to -2, which is reduction. Okay. Same question, different reaction. Well, opposite question. This time we want to identify the reducing agent in this reaction of thiosulfate with iodine. So which is the reducing agent? Is it the, well, first of all, is it going to be something on the left or something on the right of the equation? The left, yeah. The oxidizing agent and the reducing agent are reactants. They're the things that are going to do something. So you're always going to be picking something on the left. Which one is the reducing agent in this case? Close. So the other one.
Oh,
Yeah. So iodine goes from 0. To figure this out, it's best to just write it out so we know. Iodine in this reaction goes from 0 to -1. Everybody see that? It's 0 here, and it's -1 here. And then oxygen is going to stay the same, but sulfur in that other compound is going to go from, let's see. So we've got 3 oxygens is -6. We're going to, and it's 2-, so that means each sulfur has to be +2. So sulfur is going to start at +2. And then an S4O6 2-, again, oxygen is going to be -2, so that's -12 total. So we need 4 sulfurs to be +10, which is kind of a weird thing. So those are actually, there's actually something else going on there, but we can still think about it as it's like approximately +2.5. That's not exactly right, but for our purposes, we can still say that sulfur is being oxidized, so that makes it the reducing agent. So the reducing agent is S2O3. Now what about this one down here while we're talking about redox stuff? Which of these is not a redox reaction? This is a little tough because there's a lot of stuff going on here. Which ones can we eliminate right away? Which ones of these are definitely redox reactions? How do you know? Why A?
Because there's it's just hydrogen.
Yeah, anytime we see elements that are in their elemental state on one side of the equation, but then in a compound on the other side of the equation, there has to be redox going on because it has to have gone from 0 to something or something to 0. So anywhere we see elements in their elemental states, we can assume that's going to be a redox reaction. So where else do we see this? In B, we've got zinc becoming zinc 2, so that's definitely redox. And E, right? Because chlorine on one side, bromine on the other side. So those must be getting oxidized and reduced. So we can look between C and D and try to figure out what's going on here. So what do you think between those? Which one is not redox? D, why D? Because what?
Like, I don't know.
Just as a guess? Okay, so it's a reasonable guess. Who else? Other ideas? How can we figure this one out? Yeah, in this case, we'll really have to assign the oxidation states to figure it out. So D, and with multiple choice like this, we can kind of at least not have to do all of it. Like for instance, with D, it's going to be a lot easier to assign oxidation states to some of these than others. Like let's look at iron. So what's the oxidation state of iron in iron sulfate here? Well, what's the charge on sulfate? 2-, so then iron has to be 2+. And remember that metal ions, their oxidation state is equal to their charge when they're just a regular ion. So that's 2+. What about the iron in the product? What's the charge on that iron? Is it still 2+, or is it different? It's got to be different because it's got same counterion, same sulfate, but in different ratios. What's the charge on iron in Fe2SO4 3? Well, what's the charge on sulfate? Sulfate's still sulfate. So that's -2. If there's 3 of those for 2 irons, what does each iron have to be? Let's write it out. So in that compound, we've got 2 irons, Fe2, and then SO4 3. We know SO4 is -2. So what does iron have to be to make a neutral compound? +3. You see that? You see how that works? If you've got 2 of one and 3 of another, and they have to equal out, then the one with 2 has got to be 3 plus, and the one with 3 has got to be 2 plus, or 2 minus. So that tells us that this is redox, because iron went from +2 on the left to +3 on the right. And C is the one that is not a redox reaction. What's happening there is actually an acid-base reaction. So the it's not a kind that we've looked at, but it's considered an acid-base reaction. Hydrogen's always going to keep a +1 oxidation state. Oxygen -2, ammonia -3, or nitrogen -3. If we went through and assigned all those oxidation states, we would figure that out. So if you encounter a problem like this on the exam, what I would recommend is, do like we did, narrow it down, and then you think like, okay, the only way I'm going to figure this out is to actually go through and assign all the oxidation states. So then just skip it. Go on and do other stuff. Come back to it at the end, and if you still got half an hour or something, or however long it takes, then you can work through it. If you don't have enough time, you just guess one, and at least you've got a 50-50 chance of getting it. But that's a good way to approach these kinds of things, especially on our hourly exams or our regular exams. Like on Monday, we're going to have the full 3 hours in the class to work on that exam. You don't have to use that much. I don't write it to take up that much time, but if you do have extra time, that's the kind of thing you can use that time for. All right. Let's look at some, let's go back to reviewing some of our reaction math stuff, the stoichiometry stuff that we did on Tuesday. A problem like this is definitely a test type question, because you're only given limited information and you got to kind of figure out the whole question on your own. So in this case, at least they're helping you by giving you the formulas. You could also do this with just the names. But see if you can work through this one. This may be a limiting reactant type situation. It may not be, but you certainly going to have to develop your own chemical equation. See if you can work this out. It's going to take a little while.
Is this going to be a question that could be on multiple choice, or would be more of like a free response?
I would probably ask this more on a free response, but yeah. Just because if you're going to put that much work and time into a question, it should be worth more than 2 points. I feel like, yeah. So remember, you're going to need to find moles of each, and then determine if one of these is a limiting reactant, and then figure out how much product you're going to get. All right, go ahead and keep working if you're working. I'm going to start setting this one up. So we have to first get a reaction. Is that the equation you got? Okay, great. So now we got to figure out moles of each and if there's a limiting reactant going on. So. Okay, so I've got that we are given 0.019 moles. So this is where like millimoles can be helpful. If we just kept it in milliliters, we would have gotten 19.0 millimoles, 25.2 millimoles. So is that a stoichiometric ratio or is there a limiting reactant situation here?
Limiting reactant.
And what is the limiting reactant?
The CuCl2.
Yeah, so the equation tells us that CuCl2 and ammonium sulfide need to be in a 1-to-1 molar ratio because they both have ones in the equation. So 1-to-1 molar ratio, but the moles we actually have are 19 millimoles of one to 25 millimoles of the other. So instead of a 1-to-1 ratio, we have a little bit excess ammonium sulfide. So that means this one is limiting. So that's the one we have to use in the rest of the calculation to figure out how much copper sulfide is formed. Again, because of the coefficients here, it's 1-to-1 between copper chloride and copper sulfide. So we can say that we have 0.0190 moles copper chloride, or copper sulfide, sorry. Multiply that by the molar mass of copper sulfide, which would be 32 plus 63.5, right? Which is 95.5. Is that right? So about 1.8 grams, 1.82 grams. Is that what you got? Everybody do that one? All right, great. Yeah, keep practicing these. There's, of course, a lot of this kind of stuff in the Chapter 4 homework, so it's really would be great if you got that done before the exam. It'd be very helpful. All right, we'll do one more, and then we'll take a break and come back, and then we'll come back to this at the end of class if you want to do a little bit more review. Okay, so last one is this one right here. Now, this is more traditional like what we did on Tuesday, where you've got a mass of each of them. You got to figure out which one's limiting, which one's in excess. The trick about this one, oh wait, no, I was going to say the trick about this one is you need to figure out the equation, but it's given. So there's your equation. So you just got to calculate it, figure out which one's limiting, and what mass of the excess reactant would still be present after the reaction is complete. Give that one a try.
The excess reactant present in this. But the answer, I know that there would be some energy.
So, I mean, we can go through how to solve this, because what you need to determine how much stuff based on so like what is Based on what? Based on each one? Okay, so if this is how much you're using, this much of the other one,
Yeah,
and if you use this much of this one, you use this much of the other one.
yeah.
So yeah, so that's more than that. So how much is just the difference between this and how much you actually use.
So this one is that.
Yeah.
Okay.
You also think of this like sense.
No, because he was like, wait, yeah, maybe that was not right.
Yeah.
Yeah.
All right, take another minute or so and go over it. I'm going to copy this over to another spot here so we can have a little more room to write on it. All right, so we've got our equation here. So now we've got to start solving it just like normal, where you convert to moles and then figure out how much of the other one you would need. I saw in some people's work that you converted one all the way to the grams of the other. That's a more direct comparison rather than going to moles. And so let's do it that way. If you didn't like the way we did it on Tuesday, here's another way you can do that. So you would take 41.0 grams of magnesium. And we're going to go from grams of magnesium to moles, and then actually go all the way to the other reactant, which is iron chloride. So moles of magnesium, moles of iron chloride, iron 3 chloride, and then all the way to grams of iron chloride. So magnesium, 24.3 grams per mole. The equation tells us 2 of these for 3 of these. And then anybody have, oh, it's given right here, the molar mass of iron chloride 162.2 per mole. So that's 41 divided by 24.3 times 2 divided by 3 times 162.2, 182. Tells us that if we're going to use all that magnesium, we need 182 grams of iron chloride. How much iron chloride do we have? Iron 3 chloride do we have in the equation? It's not that much, right? So what does that tell you as the limiting reactant? Yeah, the iron 3 chloride. If you don't have as much as you need, then that one must be limiting. So this is saying if we used up all the magnesium, all 41 grams of magnesium, we would need 182 grams of iron 3 chloride. That would be our stoichiometric ratio. Since we have less than what we need, then the iron chloride must be what we actually are going by. And so that one is limiting. So that means it's going to be either C or D. Now there's an easy way to answer this, but let's go through and calculate it anyway, because not every question is going to have this thing. So what we have to do, that means since iron chloride is limiting, we have to do the calculation based on that instead. So we do the same calculation, but starting with iron chloride and going to magnesium instead. So 175 divided by 162.2 times 3 divided by 2 times 24.3 is 39.3 grams of magnesium. So that calculation says if we use all 175 grams of iron 3 chloride, then we need 39.3 grams of magnesium. And we have more than that. We have about 2 grams more than that. So our answer must be C. The limiting reactant is the FeCl3, and we've got about 2 extra grams of magnesium. So how could you answer that question? Once we've narrowed it down to know that the limiting reactant is iron chloride, how could we have avoided that second calculation? Anybody catch this? Okay, it's not always going to be this way, but in this particular question, this is the nice thing about multiple choice. Once you narrow it down to C or D, so you know the limiting reactant is FeCl3, and so either 2 grams of magnesium remain or 87 grams of magnesium remain. Why doesn't that 87 grams make sense? Yeah, we only started out with 41 grams, so we couldn't magically make a bunch more magnesium at the end. So the only one that would make sense would be C, that there would be 2 grams remaining. See how that helps us, saves us a couple minutes. Not a big deal, we can always do that calculation. But all right, let's stop there and take a break, and then we'll come back and look at some other stuff. Okay. So we're going to talk a little bit about gases. To do that, we need to know something about pressure. I mentioned this before when we were doing an equation on Tuesday, but when you measure out gases, you can weigh them if they're heavier than air. If they're not heavier than air, it makes them really hard to weigh. And they're kind of hard to weigh anyway because they can be compressed. You can't really, they take the volume of their container, so it's hard to measure them that way. So often the way that we measure quantities of gases is by pressure, by the pressure that they exert. So anybody remember from physics, what's pressure? Well, those are the units, but like, what is it? So, go ahead. Go ahead. A force? Almost. It's a force applied. Pressure is not actually a force. Pressure is a force applied to an area. So when, like, for instance, if you're standing on the ground, let's say you're standing out in the grass and you got your regular shoes on, and then you change into shoes with really pointy heels. What happens? You sink into the ground. So the force hasn't changed because you're still you. You're the same mass. The gravity's the same. You're pushing down on the ground with the same amount of force. So what's changed between having regular shoes and having pointy shoes?
The area.
The area, yeah. The pointy shoes are a much smaller area. And so like when I wear pointy shoes, they sink down into the grass even though I have the same force. So pressure is not exactly a force. It's a force applied over an area. When we talk about gases, does anybody know what creates the pressure of a gas? Yeah, collisions of molecules. So we say like when a gas exerts pressure on its container, we talk about that as defined as collisions of gas molecules with container walls. And we'll get into that more in the end of the chapter when we talk about the kinetic molecular theory. But the gas molecules are hitting the walls of the container, and that's creating a force applied to the area of the container, so pushing against the area. All right, so now let's talk about the units of pressure that we usually work with. So somebody said pascals. Okay, that's one unit. Pascal is kind of like the SI unit, and it's defined as a Newton per meter squared. So the Newton is a force measurement applied over a square meter. That's a Pascal. Of course, since it's a metric unit, we can talk about kilopascals or millipascals or megapascals or whatever, or we can apply whatever prefix you want to it. So that's one. What are some other units of pressure that we'll use? Anybody know some? Yeah, so there's another kind of weird one, millimeters of mercury. This is also known as torr. How can we measure pressure based on millimeters? Because millimeters is a length measurement, not a pressure measurement. Anybody know where this comes from? I'll show you a picture. This comes from this device known as a Mercury Barometer. So if you have a tube that you have evacuated, taken all the air out, and you put it down in a bath of mercury, don't actually do this because mercury is poisonous, and it has a high vapor pressure, which means even if there's mercury just sitting there, there's a lot of mercury vapor coming off of it that you can't see. So even just being around mercury means you're inhaling mercury vapors. So it was a bad idea for them to do this, but they didn't know, so at least we learned some stuff. And I don't think anybody, I don't know if they died from mercury poisoning or not, but don't do this. So anyway, if you do this, the atmospheric pressure pushes down on the mercury in that container, and it pushes it up the tube. And the distance it pushes it up the evacuated tube is that millimeters. So 1 atmosphere, like the pressure of the atmosphere at sea level can push that mercury up 760 millimeters. So that's where the millimeters of mercury comes in. You can also have inches of mercury. Inches of mercury is how we usually talk about pressure, like barometric pressure, the pressure of the atmosphere that in like a weather report, when we talk about areas of low pressure or high pressure. High pressure is usually associated with less precipitation. That's usually measured in inches of mercury. So like standard atmospheric pressure is 29.9. If we look today at the weather, is this in the right spot? Sure. So you might pull up your weather forecast, and the pressure is given right here as 30 inches. So that's 30 inches of mercury barometric pressure. And you can actually see the change in pressure. So let's see, the black line here is pressure over time. So today, pressure is supposed to drop quite a bit, go from 30, what it is right now, down to below 30, 29.7, 29.8. And that lower pressure indicates the front coming in and the thunderstorms developing tomorrow. Wow, 90s next week.
Oh, yay.
Ugh. Oh well. Anyway, so that's some other measurements of pressure. And then the other one that we'll use a lot is atmospheres, ATM. Okay. So 1 atmosphere equals atmospheric pressure at sea level. Then the last one we see probably also commonly, there's some other weird ones, but the other common one would be PSI. Pounds per square inch, which can also be written as pounds over square inches. So it's kind of like the Newton per meter squared, the pound per inch squared. So the imperial units or the English units equivalent of that. And of course, that's how we measure things like tire pressure. All right, so that's a bunch of units. Let's put a little conversion chart here. You don't have to know all these numbers. I'll tell you which ones you do need to know. You need to know that 1 atmosphere is 760 millimeters of mercury. That's an important conversion. And we'll use that a lot. And chances are you won't have to spend a lot of time memorizing that. It'll just be in your head from all the times that we use it in these calculations. And then the other ones, let's take a look at the other ones just so we have a sense of how big they are. You don't need to know these. Okay, so an atmosphere is about 101 kilopascals. .92 inches of mercury and 14.7 psi. So make sure you know this one. The other ones will always be given if you need them. And I don't, yeah, so the millimeter of mercury is actually an exact unit. It's defined as 760 millimeters of mercury per atmosphere. So that's not 2 or 3 significant figures, that's infinite significant figures for the 760. All the other ones are measured numbers. So those would be, you'd have to look it up for however many significant figures. That one is exact. All right, so that's pressure measurements. So let's take a look at some of these relationships that you've hopefully heard before, dealing with the different quantities that we can measure pressure, or that we can measure gases with. So in here, we're going to be looking at when we change one factor, what happens to the other. So how are volume and pressure related? You know, what happens if you got a sample of gas at a particular volume and a particular pressure? Okay. These things are hard to open. There you go. So if you got a sample of gas at a particular volume and pressure, let's say you got a balloon filled with gas. If you increase the pressure on the balloon, what happens to the volume? Does it go down or up?
If you increase the volume.
Down. If you increase the pressure, what happens to the volume? It goes down, right? You squeeze it, it gets smaller. That's the volume going down. So we might say that when pressure increases, volume decreases. That'd be probably a fair way to say that. Let's see. There's probably a picture in the book here that we can put in here. Yeah. Okay. So if you've got a sample of gas, this is kind of like a syringe type model. If you block the bottom, you've got a bunch of gas in there, you push it down, you've got the same amount of gas, but now the pressure is increased and the volume is decreased. The volume has gotten smaller. So we can talk about it that way descriptively, but we can also look at it mathematically. So we could say the pressure is exactly equal. We would say the pressure is inversely proportional to the volume. So if we increase pressure, volume has to decrease to compensate. And the opposite is true as well. And then another way to express that is that the product of pressure and volume is always constant. So if you multiply the pressure and the volume together, you always have a constant, so that if the pressure increases, the volume has to decrease. If the pressure decreases, the volume has to increase, so that the product of the two is always the same value. And this is known as Boyle's law. Since the pressure and volume are always constant, if you change one, the other one has to compensate. We can actually calculate for that. So like over here, we can think of this as an initial volume and an initial pressure. And that has to be the same as the product of the second volume and the second pressure. Graphically, that's going to look like, oh, not that. There. Yeah.
What, is that like an alpha? Or
Yeah. I just mean like it's proportional to, because it's not equal to 1 over b, because there's a constant involved.
And I have another question.
Yeah.
So you're talking about like the balloon example, but when you're talking about
that, I was picturing like, as you blow up a balloon, are you increasing the volume and pressure?
Maybe. But you're changing something else too, because you're changing the amount of gas that's on the inside. So there isn't really a third thing. Eventually we're going to put this all together, but yeah. So you're not only changing the pressure or the volume or both, you're changing the amount of gas that's in there. And that is actually probably truly, yes, changing the pressure and volume. But let's say you have like a balloon that's filled. If you increase the pressure by squeezing on it, the volume would go down, it would get smaller. Any questions? So that's an exponential decay type curve, which just means that, or it's a hyperbola. It's not exponential, it's hyperbolic, which shows that relationship. It's an inverse relationship. And those are some different ways about talking about the relationship between pressure and volume. Okay, any questions about pressure and volume? Think of some example in your head to keep that straight, like whether it's a balloon or a plunger or whatever. Let's look at the next one. So the next one's going to be volume and temperature. Okay. So this time, we're going to keep pressure constant, which means we need to think of something that can change its volume or change its pressure. And actually a balloon is a decent example of this, because if you imagine the balloon can expand with limited resistance, what happens if you increase the temperature of a sample of gas? What's going to happen to the volume? It's going to expand because the gas expands, right? So if you cool down a balloon really, really cold, and we don't have any liquid nitrogen right now, but we can try this maybe, I think, next week or the week after. If you cool down a balloon really cold, you should be able to make it shrink up. And then when it comes back to room temperature, it should come back in the same way. Oh, well, there's a picture of it, so that'll be the next best thing. So you've got your gas molecules in there. In ice water, it's going to be small. In boiling water, the molecules are going to be moving a lot more, and so the container expands to accommodate them. This one's pretty intuitive. You can just think about it as gas expands, which means increases volume. When heated, and heating increases temperature. So this tells us that there's a direct relationship. When one goes up, the other one goes up. The volume is proportional to temperature. One goes up, the other goes up. One goes down, the other one goes down. That's the opposite relationship of Boyle's law, which was an inverse relationship. And we can write these things all the same using the same types of language that we did in the previous. It's just all going to be opposite. So we might say that V divided by T is always constant, if we rearrange that equation a little bit. We could also talk about volumes and temperature like this, where the first volume divided by the first temperature has to equal the second volume divided by the second temperature. So in this particular example, they both go up. So the ratio between them stays the same. One goes up, the other one goes up. And this is known as Charles' law. Okay, that's one we're going to look at. So we can also think about, since pressure is held constant there, we can also talk about volume being held constant, the relationship between pressure and temperature. It's not really a separate law because it's the same kind of thing. It does have its own name, but we're just going to assume that it's basically the same. And we're going to put all these together in the ideal gas law in a minute anyway. So let's look at the last part of this, which is the relationship between volume and amount in moles. Okay. So if you put more gas into a container and the pressure stays the same, what happens to the size of the container? You put more gas into a container, the pressure has to stay the same, what happens to the volume? It increases, so this is like blowing up a balloon. If you're assuming that the pressure is staying constant as the balloon expands, then what you're doing is you're putting more gas in and increasing the volume of the balloon. So that's another direct relationship. So under constant pressure, volume will increase when number of moles increases. So volume increases as number of moles increases. And that just kind of makes sense. You know, blow up a balloon, increases. So why is it number of moles and not mass? What's going on with that? You know? Yeah, because it's the particles. In a gas, the space between molecules is so big that we don't actually have to consider the size of the molecules themselves. So it's not so much the mass that increases, it's the number of particles. Even if those individual particles are really, really heavy, if you have more of them, that's going to cause the effect rather than how heavy they get or how light they get. And an interesting way of kind of showing this, we can look at this reaction where oxygen gas is converted into ozone gas. So O2 goes into O3. That's not balanced, right? So we're going to balance it. We need 3 of these to 2 of these. So 3 oxygen molecules become 2 ozone molecules. Let's say that reaction happens in a balloon. So you've got a balloon filled with pure oxygen, and you irradiate it with UV light and turn it into ozone. What happens to the volume of the balloon? You don't let anything out or in. You just do that reaction. What happens to the volume of the balloon?
It goes down.
It goes down. Yeah, why?
There's less moles.
Right, so the relationship is if the number of moles goes down, then the volume also has to go down. So even though you haven't let anything out of the balloon, all that oxygen has become ozone. So there are now fewer gas particles inside that balloon, so the volume goes down. So in the end of this reaction, the volume would go down. The fact that an ozone molecule is bigger than an oxygen molecule doesn't matter when we talk about gases because the actual size of the particle doesn't matter. So the fact that we have fewer particles is what is causing the effect. Fewer moles means fewer particles. So that's where that comes from. This, by the way, is called, we're done here, there we go. Avogadro's law. So here, those are the different quantities that can affect gas: pressure, volume, temperature, and amount. And so we can put that all together in something I'm sure you've experienced before called the ideal gas law. So the product of pressure and volume is always equal to the product of the moles and the temperature times a particular volume. And that's just a way of putting all those other equations together. If you want to try it out yourself, you can take all those equations, rearrange them, and put them together, like solving one for the other quantity. And this is what you end up with. The R is what you get from all those constants that end up coming together. This is called the gas constant. There's a couple different ways it can be written. The one that's probably most useful to us right now is 0.08206 liter atmospheres per mole Kelvin. The reason there's so many weird units there, constants are often like that, they have to cancel everything. So the left side is pressure times volume, the right side is moles times temperature, which means moles times temperature have to cancel, and you end up with pressure and volume, atmospheres and liters. What's important about the gas constant is that it can change based on units. So you can convert it to other units just like you would with any other value. So depending on what you're actually trying to calculate, you may be given pascals or atmospheres or millimeters of mercury or whatever. You can memorize different gas constants, or you can just convert units. It's usually easier to just know one gas constant and then convert units as necessary. It's also important to remember that temperature always has to be in kelvins. The gas constant's going to be in kelvins. Temperature always has to be in kelvins. And that's because these relationships don't work with negative numbers. So if you have a temperature scale that goes into the negative numbers, like Celsius and Fahrenheit, then those relationships we just talked about aren't going to hold anymore. So it has to be, just like pressure can't be negative in these equations, and volume and number of moles, temperature shouldn't be negative either, which means we always use kelvins. All right. So this means that we can now solve for any number of one of those quantities just using the other quantities. So let's try that. So calculate the number of moles of gas in a 3.24 liter basketball. Inflated to a total pressure of 24.3 psi. It also notes that when we actually measure like something with a pressure gauge, like a bike tire or a car tire, that's not the total pressure. That's the difference in pressure between what's inside and the atmospheric pressure. So we're not going to deal with that right now. We're just going to say, okay, so total pressure. Here's what we've got. So all these questions kind of are the same. You're given some of those quantities, either P, V, N, or T, and you have to solve for whatever you're not given. So in this case, you're given P and V, and we have to be given temperature too. So let's say at like a normal room temperature, 25 degrees C. So we're given pressure, volume, and temperature, and we have to solve for moles. The only thing that we have to remember in these types of equations is to convert units appropriately. So in this case, since we have our R in liter atmospheres per mole Kelvin, and our basketball is already in liters, there's our volume, there's our pressure, there's our temperature. We're going to want to convert that pressure from PSI to atmospheres and the temperature from Celsius to Kelvin. All right. So let's do that. 24.3 PSI. We're going to convert PSI to ATM, which if we go back up here and check that is 14.7. 14.7 PSI in an atmosphere. Is 1.65 atmospheres. (25 degrees C plus 273 for Kelvin is 295. 298. Thank you. K. All right, now we've got everything in the units that we want. We can solve for moles. So our equation is PV equals nRT. We can rearrange that to N equals PV over RT. Do a little algebra, and then plug in the quantities that we just got. So 1.65 ATM, 3.24 liters, 0.0821 for R, and then our temperature is 298 K. If you look at the units, they should all cancel, and we should just be left with moles, which we are. So let's do that. 1.65 times 3.24 divided by 0.0821 times 298. Is that right? No, what did I do wrong here? Oh, I did times instead of divided by. 1.65 times 3.24 divided by 0.0821 divided by 298. That looks better. All right, 0.218 moles of gas. This is probably, or this is one of the most useful ways of doing this type of calculation. Because if you were to say, use gas in a chemical reaction, this is how you would measure the number of moles. And once you figure out the number of moles, then you can do all the other stoichiometric calculations, limiting reactant or whatever. So we can now plug this gas stuff into the stuff we learned from chapter 4 by solving for moles using pressure and volume. And realistically, if you're doing this in the lab, that's exactly how you're going to do it. You can measure the temperature, you can measure the pressure from however you're dispensing your gas, and you know the volume of the container. And so you can calculate the number of moles of gas that you're either producing or putting into your reaction or whatever. This is how it's usually done. Okay, let's see. I think that's probably good. But let's look at one more thing, and then we'll go back to practicing for Monday. The last thing is just kind of rearranging some units and looking at density and molar mass. So let's put our equation back up here, our ideal gas law equation. And let's think about what some of these quantities actually mean. So N, number of moles, so number of moles we can think of as the mass divided by the molar mass. Right? Because mass is in grams and molar mass is grams per mole. So if you divide grams by grams per mole, you've got moles. So why would we do that? Why would we want to express the moles as mass and molar mass? Well, because mass can be used to give us some density information, and molar mass is helpful because it can help us identify a gas. So if we know the molar mass of a gas and we know something about what elements are in there, we can figure out what kind of gas it is. So let's plug this back in the equation. What symbols do the book use? I just want to be consistent here. We'll just say G for grams and big M for molar mass. So we can rewrite this as PV equals G, do it this way, GRT over big M. So that's grams and then molar mass. Because of that, what we just talked about. So now we can rearrange this a little bit, just using algebra, and say pressure equals GRT over VM. See how I did that? Just divide both sides by V. So what's the point of that? Well, what's mass divided by volume? Density, right? So now we've got the ideal gas law in terms of density and molar mass. So we can rearrange this in various ways. We can say density equals, what does it end up being? Yeah, P times the molar mass over RT. So we can calculate the density of a gas just knowing its identity, so it's molar mass, and then the pressure and the temperature. We can also figure out the molar mass of a gas by, again, just doing some algebraic rearrangements. The molar mass of a gas is going to be its density. So now we've got all experimentally determinable quantities. We can measure the density, we can measure the temperature, and we can measure the pressure, and we can figure out what gas we have based on its molar mass. So that gives us a couple other options of things we can figure out in terms of gases. So using this, like an example in the book is calculate the density of nitrogen gas at 125 degrees C and a pressure of 755 millimeters of mercury. One way to do that is just to remember an equation like this and plug it in, and that's fine. Or you can just remember the gas law and kind of go through this derivation on your own and make sure you know how to do that if something like that comes up. So this is just a way of expressing the same thing in terms of density and molar mass just by rearranging a couple things. All right, let's stop there. On next week, we'll talk about partial pressures and the kinetic molecular theory stuff. There's not a whole lot more to do there. So I'd rather use the rest of the time here to make sure everybody feels good about, well, that might be a stretch, but make sure everybody has a little more time to think about the material for the exam on Monday. So in terms of the various topics that we've talked about so far, what do you think is giving you the most trouble? What do you want to talk more about right now? Go ahead, I think I saw you first, Kyle.
Like the, I was telling you earlier, like that whole, like, you know, this percent of carbs and oxygen percent hydrogen, you need to figure out the, if you're from like the formula thing.
The percent composition,
Yeah.
empirical formula determination.
How to do those.
Okay, we'll do one of those, yeah.
Combustion analysis.
And combustion analysis.
This is just in general, but like more multi-step problems.
More multi-step
Like
problems?
78, for example.
Okay.
Like we need to write out the equation, balance it, find like the reactant. Like
Yep.
just not like that simple.
Yeah, no, I understand. Yeah,
Just
okay.
more
Let's do that too. So LL analysis, combustion analysis, the multi-step equation problems. Anything else specifically that would fit into one of those categories? Yeah.
I don't know. It's like
That's
going from like having you like have like a word problem and you have to like get the equation from like this hydrogen like getting
Yeah,
that,
so the same
formula
kind of thing.
equation,
Okay.
yeah.
Yeah. All right, we'll do that too. Okay. Let's let me go to Blackboard here and get rid of some of this other stuff. Let's slim this thing down a little bit. Let me head to Blackboard and we can take a look at some of those practice problems on the exams, and I can show you some of those. So this first exam is the actual exam from last year. I would caution you, practice exams can be a little bit old exams can be a little bit dangerous because they're not meant to be used as a study guide. An exam is just kind of a snapshot of what we were doing at a particular time during a particular class. It's going to be kind of weighted toward one topic or another just because of what happened that year or whatever. So I think a lot of people feel like, oh, if I just go through the old exam and kind of go through all the questions, I'll be okay. That's really not a great strategy. Yeah.
Does that mean that like our exam is going to be specifically concentrated on like thicker material?
Not necessarily. It's just like an exam is only so many questions, and I don't use like a strict, rigid formula to say, okay, I'm going to do 2 of this type of question and 2 of this type of question. So the exams aren't always the same. So there's always going to be stuff that doesn't make it in the exam just because there isn't room. You know, it just exams are different. So I guess what I'm saying is, when you don't think that you can just go through an exam and that's like you're studying, because there's not going to be enough on there. It's only one exam. The homework is really where you can do that. So there won't be anything on the exam that is way different from something you've encountered in those first 4 chapters of homework. And I include both the Mastering Chemistry and the book questions in that. But just the exam, just going through the exam is not a great way to do it. So what I would do is go through all your old homework, keep working on questions throughout the weekend, and maybe Sunday in the afternoon or in the evening, pull out this exam as kind of a check on yourself and make sure you can do all those problems. If there's any of them that you think like, wow, I don't even know how to start this, that's a sign that you still want to go back and review some of the, whatever that topic was. So let's take a look at one of these old ones, just to pull up some of those questions that you've been asking about. One of the things on this old one, there's like defining terms. We don't really do that. Let's see if they have a good percent composition for practice problem on here. There's some good equations. I mean, they were probably using a different book and everything, so. Oh, here's one. Yeah, so here's a combustion analysis problem. And then we'll also look at a regular percent composition type one. Okay. Compound consisting of CHNO only has a molar mass of 331.5 grams per mole. Combustion of 0.1 grams of the compound caused a whatever increase in the mass of a CO2 absorber, and this increase in the mass of the H2O absorber. So that's just a fancy way of saying that much CO2 and that much H2O. What is the empirical formula of the compound? So do you want to step through it together, or do you want to try it and then go through it together?
Go through together.
Go through it together? Okay. So in this case, we would mark all the stuff we've got here. So we've got a 0.1 grams of the compound, and we're going to have this much CO2 and this much H2O. And remember our steps here. We can figure out how much carbon there is from the CO2 and how much hydrogen there is from the H2O, and then we have to go back and do some subtraction to figure out how much oxygen. So our first step is going to be converting the moles. So we're going to go from grams of CO2 to moles of CO2. So that is 44. I know that's not the right amount of significant figures, but we should at least get close here. So that's how many moles of CO2 we have. And since CO2 is 1 mole of carbon per mole of CO2, we can also say that's the same number for our moles of just carbon. Okay, next, we're going to do the water. And then there's 2 moles of water, of hydrogen for every mole of water, right, because it's H2O. So we have to multiply that by 2 to get the moles of just hydrogen.
Why can't you do that sort of stuff like with the oxygen?
What?
Why can't you do that sort of stuff with the oxygen? Why can't you do it with carbon and hydrogen?
Because extra oxygen was involved in the combustion. Remember, combustion is like compound plus oxygen. So we don't know how much extra oxygen was involved in the reaction. So a lot of the oxygen from the CO2 and the H2O is from that extra oxygen. Only some of it is from the initial. So that's why we can't do it that way. Okay. So now we have to figure out, we have to go back and calculate grams of just carbon and grams of just hydrogen so we can figure out how much oxygen there was. So let's call this the first step. We get the moles. Second step, we get the grams of just carbon and just hydrogen. So this much carbon times 12 grams per mole. .0797 grams of carbon. Same thing with hydrogen, 0.0106 moles of hydrogen times 1.01 grams per mole. Grams of hydrogen. All right, so now we can get the grams of oxygen by subtracting those. So the grams of oxygen is going to be the total amount that we started with, which is 0.100 grams of the total compound. Yeah? We did that up here. Yeah, but you're right, we did. So it was this much water, and then we multiplied it by 2 to get this many moles. Yeah. So we're going to subtract carbon and then subtract the hydrogen. So that tells us the initial oxygen in that compound was 0.0096 grams. So now we can get moles of oxygen. Oh yeah, you're right. I'm sorry. You want me to put the grams on the bottom? Uh-oh. Oh, we're so close. Okay, we might have to shut the program down. Let's just finish with the board here. So 0.0096 grams of oxygen. And we want to go from grams of oxygen to moles of oxygen. So that's going to go 16. Okay, so now we can look at our three numbers, which are still visible, even if the program's kind of busted. 0.00664, 0.0106, and 0.0006. That seems really small. It's going to be a crazy number. Did we do something wrong here? Well, let's try it and see. So we're going to divide everything by the smallest one and see what kind of numbers we get. So 0.00664 divided by 0.000, oh no, that's probably about right, 6, it's about 11. So that tells us C11. For H, it's going to be 0.0106 divided by 0.0006. So it's 17.67. And then O1, because we divided that by 1. So assuming we did everything right, we've got to multiply this to get it to an even number. So if we multiply that by, say, 3, we get 53. So we could say this is C33H53O3. I don't know if that's right, if we did something wrong. Are the answers posted on this one? Yeah. This is super old. I don't even know who.
That is like, it looks like one of those document computer things.
Yeah, I don't even know. I don't know who wrote this or where it came from.
They had to fax this, it seems like. Nope. They got 17.5.
So what do we do differently? Oh, it was because we were lazy with our significant figures, I think.
Yeah, big difference.
Yeah, so if that's why these problems always have so many significant figures. If you do it right, then that number, instead of coming out to whatever 17.67, it would have come out to 17.5, and then we would have just been able to multiply it by 2. So, lesson learned: don't be lazy with your significant figures on these types of problems. Okay, now we're gonna have to close this program and start it up again. Well, at least the gases stuff got saved. We should probably use a new thing for this anyway. Okay. All right, so you still want to do a mass percent one too?
Yeah.
Okay. So these are hard to just like make up off the top of my head because you need numbers, but I will,
You like actual, like, numbers.
right, I'll look one up though. Okay, let's try this one. Vanadium forms oxides with percent by mass 76%, 68%, 61%, and 56%. Determine the molecular formulas. Or I guess it would be empirical formulas. Because we're not given molar masses. All right. So to do this, we're just looking at two elements, vanadium and oxygen, because they're vanadium oxides. And these are the percent vanadium. So let's just, we don't need to do them all, or maybe we do, but we'll do some of them and see when we get bored. So let's look at the first one. So vanadium is 76%, which tells us oxygen is what? Yeah, 24. Okay. So first step is going to be to convert those to grams and solve for moles. So if we have 100 grams total of the compound, we can say 76 grams of vanadium, 24 grams of oxygen. And we can convert those to moles. So vanadium is 50.9 grams per mole. Oxygen is 16 grams per mole. So that's 1.49. And 24 divided by 16 is 1.5. Oxygen. So what's that formula going to be? Yeah, it's going to be 1 to 1. So we divide each by the smallest one, which is, they're both basically the same number. So that's just going to give us VO. We do that for the next one. It'll be 68 and 32. Same procedure. So we're going to go 68 and 32. Numbers are all the same, so I'll just calculate the mole. So once again, oops, 68 divided by 9, 1.34. Divided by 16, 2. So that's not even number there, so we're going to want to multiply that. 1.34 times 3 gives us about 4. So that's going to give us V4O6. Or we could actually call that V2O3.
Your formula is the smallest one. Correct?
Yeah. You want to keep going to the other ones, or is that good?
Yeah, let's do a C.
Okay, let's do C. So in this case, we've got, what was C? 61?
Yeah.
So that one's going to be VO2. 2.4 divided by 1.2 is 2.
That might be harder than it kind of would be.
I mean, that's how all these problems are. So you convert to moles. When the combustion one's a little trickier because you got to go back and do the oxygen thing. For the mass percent, you just convert those percents to moles, assume 100 grams, convert the percents to moles, and divide by the smallest number. And that's it. Multiply if needed at the end. Okay, let's look at a nice big meaty problem. Or we can practice some of this stuff. Okay, a 25.0 ml sample of a 1.20 molar potassium chloride solution is mixed with 15.0 mLs of a 0.900 molar lead to nitrate solution. How much precipitate is formed? Okay, so let's take a look at this. A lot of stuff going on here. 25 milliliter sample of a 1.2 molar potassium chloride solution mixed with a lead nitrate solution. How much precipitate is formed? So what do we do first? What would you do first? Yeah, we got to set up a chemical equation here because we don't know what we're going to do until we at least have a chemical equation to tell us the relationships between the stuff. So how do we set that up? What's the reaction here? What's one of the reactants? KCl, potassium chloride, and it's a solution, so that's going to be aqueous KCl. What's the other reactant?
PbNO3 RC2.
Yeah, lead nitrate, which is going to be PbNO3 2. Okay, and it hasn't said anything about the products, so we have to figure that out. What products are going to be formed here? Potassium nitrate will be one because the K goes with the NO3. And is that going to be aqueous or precipitate? Yeah, that's going to be aqueous. Potassium ions, potassium salts are always soluble, nitrates are always soluble. So we know that one's soluble. So the other thing must be the precipitate, which is going to be what? yeah, lead chloride, lead 2 chloride, PbCl2. And that's going to be our solid precipitate. Is that balanced?
No.
So we should balance it.
2 on the KCl, 2 on the KO.
Okay, that looks good. Okay, and now we have a little bit more information about what we need to do. We're given the amount of potassium chloride and lead nitrate, and we need to solve for how much lead chloride is formed, lead chloride precipitate is formed. See Monday. So we can do that. How do we get what do we do next? What do we need to do next here? But yeah. Right, so we got to find the moles of potassium chloride and lead 2 nitrate so we can figure out if one of these reactants is limiting or how we're going to do the rest of the calculation. So how do we get the moles of each of those? Yep.
Convert the milliliters to liters and then multiply them by the molarity.
Right, convert milliliters to liters and multiply by the concentration. So for KCl, that's going to be 0.0250 liters times 1.2 moles per liter. Okay, so 0.0300 moles of KCl. For lead nitrate, that is 0.0150 liters times 0.9 moles per liter. Okay, so is this a stoichiometric situation or is there a limiting reactant here? Yeah, which one's limiting? Well, let's look at it. So if the ratio in the equation tells us for every 2 of these, we need 1 of these. So we need exactly half the number of moles of this one as KCl. So we have 0.03 moles of KCl. Is this exactly half? Is it less than half or is it more than half? It's less than half, right? So that means that this one is in excess and this one is limiting because we have less than what we need. Or we could flip it around. Let's talk about it the other way. We need twice as much KCl as lead nitrate. We've got 0.0135 moles of lead nitrate. We've got more than twice as much KCl. So that must mean this one is in excess. Once you figure that out, it's good to mark that just to remind yourself in the heat of the exam and all. All right, so once we've figured that out, we can use the moles of the limiting reactant to solve for the moles of whatever the question is asking for, or the grams in this case. This should be specified, let's say it was in grams. All right, so then we set up the conversion just like normal, where we're given one thing and we solve for one on the other side. So let's see, I'll just do it up here. 0.0135 moles of lead 2 nitrate. That's a 1-to-1 between lead nitrate and lead chloride. And then the mass of lead chloride we have to calculate. So that's going to be 207.2 plus 35.45 plus 35.45, 278.1. So we formed 3.75 grams of lead chloride precipitate. So think about what we did there. We set up the equation. We solved for the moles of each of the reagent or the reactants. We figured out which one was limiting in excess or excess, and then we solved for whatever we wanted to solve for the theoretical yield in this case of the precipitate, 3.75 grams. Yep, you can do that. These questions are tough because there's a lot of potential places to go wrong. If you write down one of those formulas wrong, then the whole equation isn't going to balance right. The mole ratio is going to be off, and then everything else is going to be wrong from there. Yeah.
If you get like ratios wrong or like formula wrong for response, like would you like immediately like count it wrong? Or if we use that formula and like do like all the processes, like
I'll just immediately set your test on fire. No, that's, make sure that you, when you solve a problem like this, lay everything out as neatly as you can, because I will look through it. Like, if you made one mistake at the top and everything else was good, I'll still give you most of the points. But if there's just like some wrong number listed there, and there's no clear like word or clear how you step through it, I can't really, like I'm not gonna go through and try to figure out all your weird scratches. So yeah, just lay it out nicely in order, you know, write all your units out, write all your multiplication out, and that way if something is wrong, I can say, oh yeah, okay, just missed a decimal place here, or just got a formula wrong here. It's still worth most of the points. All right, 15 more minutes. What do you want to do? Go home, take a nap. All right, get some sleep, happy studying. I'll be around all weekend, so you can send me messages on Remind or through email if you have questions. And we'll start the exam right away on at 11 on Monday. Bring a calculator, bring something to write with.
I'm doing something after the exam.
I'm not doing anything after the exam. So once you're done with the exam, you can go on Monday. Bye.
Have a nice weekend.
Thanks, you too.